Hello everyone again and welcome to my channel. On our previous video we looked at the 18 electron rule involved in choosing ferrous metals that actually form a fantastic complex in terms of how stable that complex is and how that complex could be a potential ideal catalyst. We dove into various elements in the transition metals, like for example we looked at nickel, we looked at palladium, and we looked at platinum. I also looked at chromium. So all those were some of the interesting ones we dove into, and in here we're going to be talking specifically about the ligands and how ligands can actually attach to ferrous metals in a different ways or a couple of ways in our for we to see how that will actually increase or influence the reactivity of the ligand with that particular metal. Now, in addition to this, each additional points of attachment between that particular ligand and that particular metal is actually meaning that we are actually donating electrons to our metal or vice versa. So in here we're going to be looking at how this is actually done and what are the notations that are actually used in standard chemistry to understand this particular message. Now, one thing you guys have all looked at in various articles or documents or journals is this particular name, Hapoto number. Now, you're asking me, what is Hapoto number? Okay, let me just give you a symbol that's kind of familiar to you. So we have a symbol which is eta, which is a Greek letter word, and this is actually telling us that, hey, we are actually showing the number of atoms that are actually involved in the bonding to our metal. Let's take for an example. We have this particular metal coordinating with our compound in here. This compound is a methyl group, so in here we are dealing with a sigma bond in this case, so we are representing this as eta to the power of 1. Why? Is because we just have one atom coordinating with our specific metal in here. Now let's take another example. We have a specific metal in here coordinating with our alkyl here. So what we have is a carbon and carbon double bonded with each other, and now this double bond is actually coordinating with our metal. So in this case, how do you represent this? We represent this as mu, or sorry, you see, it's not mu. This is actually eta to the 2 because we have two atoms that are actually coordinating with our metal, or you can say 2p orbitals are actually coordinating with our metal. So this particular Hapoto number actually reveals the differences in the bonding between two complexes. So let's take for example, we have a simple sigma bond between our metal and alkyl group. So in this particular case, an example will be a griynard reagent where our R group is attached to magnesium and this is actually attached to bromine. So in this particular case, we are actually influencing the focus of our sigma complex, because our sigma complex is as a result of the sigma bond between our metal in here and our R group. So in this particular case, the notation that you can actually refer this to is something like a metal coordinating with our R group, and this is actually done with the help of our sigma complex in here. So in this particular case, we are able to actually look at a simple sigma bond metal to alkyl group, and this particular example is a griynard reagent. Now number 2, which is another way in which bonding is done between two complexes, is actually an alkene complex with bonding to a p orbital only, which shows that the metal sitting in the middle of the pi bond between the two complexes is represented as this particular name, which is the pi complex. So once p orbitals now are now used, then we can now talk about pi complexes. Now there are two ways to actually approach this. We can generate charges in our way to increase the p orbitals in the system, or we can just look at a ring and actually look at the double bonds that we have, which represents the p orbitals, and then we can actually introduce some fantastic complexing with our metal. Now let's look at the first case scenario. We have a charged particle or our charged ligand in here, and this charged ligand in this case is shown as this particular case where we have a specific type of metal actually coordinating with the two lobes. So these two lobes here tells us that, oh, we actually have an alkene actually coordinating with our metal as shown in here. So this is actually the molecular orbital diagram that's happening between our metal and our alkene, which we have over here. So an example of this is the generation of a charge on this particular compound, an allyl, I would say, either negatively charged or positively charged. So an example of this is this particular compound in here, where we have our metal actually forming a sigma bond with this carbon, and this carbon is actually attached to a double bonded carbons in here. Now take note that why am I putting the charges, or why am I generating charges? The reason why is because I'm trying to introduce an empty p orbital or here, or I'm trying to introduce a p orbital that has two electrons in it in such a way that there'll be a nice flow of electrons going from 1 to 2 to 3 carbon, or the same thing applies in this particular compound in here. So by that way, if I'm putting two electrons here, the electrons could be donated to our metal to form a sigma bond, and then what we have in this case is just one atom coordinating with our metal. So this is represented as eta to the power of 1, and this is called the sigma allyl case. Now on the other side, we can actually have a case where we have our metal coordinating with all three in here. So what we have is this dotted line showing the electrons that is actually influenced by all three atoms coordinating with our metal. So in this particular case, the dotted line starts from 1 to 2 and ends in 3. So in here, our representation will be eta to the power of 3, and this actually is called now a pi allyl. Why is it pi? Because in here we are now involving the p orbitals in here to actually coordinate with our metal. So this actually comes in two ways. We can actually do this either by generating a cationic allyl complex where we have 1, we have 2, and we have 3. So all these are all homos in this case, and they complex with our metal in here, where this is actually positively charged, and this is an allyl cation complex. And we have the other case where we have a negatively charged form, where we have all the lobes to be in phase with respect to each other, and they all coordinate to our metal, which in this case is called the allyl anion complex. So that's about it for this particular section, and another one you can actually add to this repertoire in here is using rings, and in this case we are using a cyclopentadiene in here, and since we are using this, we'll go to subject this to having a negative charge in there. And why am I introducing that in there? Because I want to increase the number of p orbitals such a way that electrons can flow by conjugation in this particular case in here. So if I subject this to a metal then I can have a couple of ways to actually form a complex. We can have a sigma state where we just have one coordination in here and these p orbitals are not involved at all, or we have another case where we can increase it by going 3 atoms coordinating with our metal in here to form our pi complex, and this is represented as eta to the 3, this is eta to the 1, and this is our sigma complex. And finally we have where all 5 atoms are actually coordinating with our metal in here, and what we have in this case is a pi complex as well with an eta to the power of 5. So that's about it for these 2 examples that shows how charges generated on a ligand will actually influence its coordination with a metal. Now the other case is when we have a neutral species, and this neutral species specifically is coordinating to our metal, and the neutral species in this case will be a ring that has a full coordination system, and an example of this is cyclooctatetraene. So in this case it's unsaturated ligand that contributes its electrons up to a particular metal. So an example of this is this particular sticker note in here, and what we see in here are all the possible ways by which a metal can coordinate. This metal can coordinate with 2 here in the form of mu or eta to the power of 2, and this is all pi complexes, all 4 are pi complexes in here. Now the next one we are increasing to 4, so in this case I have eta to the 4. Next in here we have eta to the 6, because we are using 1, 2, 3, 4, 5, 6 all coordinating with our metal, and in here we have all the 8, which is eta to the 8 coordinating with our metal. So all of them here are all pi complexes, and this compound here specifically is a neutral ligand, so you don't need to generate a charge for this compound to actually form a complex with our metal. So that's about it for this particular video. I hope you're able to understand the notation and how we can be able to see how well we can actually form complexes with our metal with respect to a ligand, and the possible ways we can go about that. All the same, thanks for following me through this long video. Truly appreciate it. Hit a comment down below, let me hear your thoughts. Hit the like, share, and subscribe, and peace. Bye.